All right, so now let's take a look at this new concept here, standard states. Do you guys remember what standard states are? Something that you learned in General Chemistry 1, also related to thermochemistry, chapter 6.
We saw this last time. It's like temperature and like.
No, that's a state function.
Right, that was the state function. So yeah, this is standard states. All right, so standard states, by definition, it's the state of a material at a defined set of conditions. So you can think of this like a frame of reference, right? So if you're measuring the height of a mountain, right, in Colorado versus a mountain in, I don't know, in Guatemala or something, how would you compare the two mountains? What would be your frame of reference?
I guess the equator?
It would be sea level. Right, so that's why whenever you say this is the height of this mountain above sea level, because that's your frame of reference. Okay? So for a gas, right, that frame of reference is pressure, and it's exactly 1 atmosphere. Okay? For a liquid or a solid, that frame of reference is 1 atmosphere and 25 degrees Celsius. And for a substance in solution, aqueous solution, its concentration, which is 1 molar. Okay. So now that we've defined standard state, we can make comparisons a lot easier. Right? So standard entropy change for a reaction is delta S reaction. So this degree sign up here is, it means that it's under standard conditions. Okay. Again, this is the change in entropy for a process in which all reactants and products are in their standard states. Okay, this is the equation here. All right, so you're basically taking the difference between the total entropy of the products and the total entropy of the reactants in their standard states. So whenever you're performing a comparison, you have to simplify it. So you can't just combine all 3 different things,
So
3 different variables.
Okay.
All right, so how do we find the standard entropies of reactants and products, right? So these right here are the standard entropies, right? But before we get there, we have to introduce this new concept, standard molar entropies. So these are also known as the standard molar entropies, meaning you have the standard entropy for 1 mole of a substance. Okay, molar entropy. All right, so you don't actually have to calculate the standard molar entropies. All right, so these standard molar entropies will be given to you in a table. So the only thing you need to know is how to use them, right? So here's an example of different values of standard molar entropy in different physical states, right? So we have solids, liquids, and gases. Do you think that gases would have lower or higher standard molar entropies than solids? It'd be higher, right? Because you have solids, lower entropy in general, and gases have higher entropies in general. So if you look at the gases here, for example, they have a lot higher values compared to the solids, right? Hydrogen gas is at 131 joules per mole Kelvin, whereas magnesium oxide, which is solid, is only 27 joules per mole Kelvin. And so the physical state matters whenever you're determining whether the standard molar entropy will be greater or lower for or between substances. Okay. All right. So before we talk about delta S of reaction or how to calculate delta S of reaction, let's focus on the third law of thermodynamics. Right. So according to the third law of thermodynamics, the entropy for a perfect crystal at absolute zero, right, absolute temperature 0 Kelvin, is going to be 0. So the entropy of a perfect crystal is 0 at 0 Kelvin. Okay. But most substances are not perfect. Right? Maybe all substances are imperfect. So for an imperfect crystal, there's always going to be some energy coming from the entropy, all right, at absolute 0. Remember that molecules at 0 Kelvin, they have 0 kinetic energy, but they have a lot of potential energy, right? But they also have some energy coming from entropy. So for that reason, the absolute entropy of substances is always going to be positive.
Is that like the absolute value thing they teach you in like ninth grade?
It's similar, yeah, absolute value. So that will always give you a positive value. So we defined standard molar entropy earlier, right? I mentioned the standard molar entropy values are for 1 mole of substance at 25 degrees Celsius or 298 kelvins. So this is the standard condition, right? Has to be 1 mole of the substance at 25 degrees Celsius. So these values, standard molar entropy values, are affected by 5 different factors. Okay, we talked about 1 earlier. That's the physical state, solid, liquid, gas. Right, so that would be the physical state, the allotrope. Anyone remember what an allotrope is?
Like a crystal, like a lattice structure.
It's related to the crystal lattice, yes. So an allotrope is basically when you have 2 substances that are made up of the same element, right, but different crystal structures. Okay? They have different atomic arrangements. An example is diamond and graphite, right? Both made up of carbon, but one has a 3-dimensional crystal structure, whereas the other one is only 2-dimensional. All right, the third factor is called molecular complexity. So how complex the molecule is. So this is usually related to the number of atoms within that compound or substance. All right, so for example, if you have H2 versus H2O, then H2O has 3 atoms versus H2 only has 2, right? So as the number of atoms increases, the molecular complexity also increases. Okay. It also depends on the molar mass. And finally, the degree of dissolution. So this is basically the extent of dissolution. So a solid, right, versus a dissolved sample. Now let's look at these 5 factors in a little bit more detail, right? Factors that affect the values of the standard molar entropy. So we mentioned the physical states, right, from solid, liquid to gas. Solids typically have lower entropy than liquids, and liquids have lower entropy than gases. So it's the same idea for standard molar entropy. An example here is liquid water versus water vapor. You can see that water vapor has more than twice the value of liquid water. The next one is molar mass. I guess before we get to the molar mass topic here, why is it that gases have larger entropy values?
The particles are more spread out than any other type of matter.
Right. So the particles are more spread out, the randomness is higher, right, compared to liquids or solids, because solids have very specific structure, so they're fixed in place, not moving at all. All right, the next one is molar mass. So the higher the molar mass, the greater the entropy, right? And molar mass has less effect on entropy than the physical states. So an example here is group 8 elements, right? The noble gases. So you have helium all the way down to xenon. So when you look at the value for for helium is 126 joules per mole Kelvin. But for xenon, which is a lot heavier, it's 169.4. And this is due to the number of subatomic particles, right? So xenon has a lot more protons and electrons compared to helium, which only contains 2 protons and 2 electrons. All right, and the third example here is allotropes. All right, so another factor that affects the value of standard molar entropy. So again, allotropes, by definition, are elements that can exist in multiple forms. For example, diamond versus graphite. Okay, so for the less constrained structures, they have greater entropy. So graphite right here has less constrained structures because they're basically just a bunch of carbon sheets stacked on top of each other, right? Versus diamond, they're 3-dimensional, so they have that phase cubic center FCC type of crystal structure, and so they have lower entropy. So the fourth one here, the fourth factor, is molecular complexity. So as I mentioned earlier, as the number of atoms increases within a molecule, it becomes more complex. And so the more complex the molecule, the higher the entropy. Okay? For a given state of matter, whether it's solid, liquid, or gas, entropy generally increases with increasing molecular complexity. So for example, argon versus nitrogen monoxide. Right? So we know that argon right here has a higher molar mass, but nitrogen monoxide is more of a complex molecule because it contains 2 atoms, right, versus 1 for argon. So when you look at the value of standard molar entropy here, we have 210 for nitrogen monoxide and only 155 for argon. All right, comparing nitrogen monoxide and carbon monoxide. So they both have the same number of atoms, except nitrogen monoxide is slightly heavier, right? It has slightly higher molar mass. And because of that, the standard molar entropy of nitrogen monoxide is also slightly higher than that for carbon monoxide. Okay. And looking at the fourth example here, we have ethane, C2H4, so that contains a total of 6 atoms, which has a low molar mass but pretty high standard molar entropy. And the last factor here is the dissolution. So dissolved solids versus undissolved solids, right? So dissolved solids would have larger entropy compared to undissolved solids. So an example would be between solid potassium chlorate and aqueous potassium chlorate. Right? So the aqueous one, the dissolved salt, has higher standard molar entropy than the solid one, which makes a lot of sense because if you look at the number of moles, right? So let's say we have KClO3 solid, and if you dissolve this in water, this dissociates into K plus and ClO3 minus, right? And so in the solid form, we have 1 mole. And in the dissolved form, now this is aqueous, we have 2 moles. So that increase in the number of moles results in an increase in entropy. All right, let's take a look at this example. Arrange these gases in order of increasing standard molar entropy. So we have sulfur trioxide, krypton, and chloride gas. So let's see. Maybe I'll ask Zoe first. Which one of these three has the highest standard molar entropy?
I don't know. I'm
Well-
gonna go with, I don't know, I'm gonna go with SO3, but I'm probably so wrong, so.
Well, that's a good guess. It is correct. So it's sulfur trioxide because it contains the most atoms, right? It's the most complex molecule here. So SO3 has the largest standard molar entropy. What about the molecule with the lowest standard molar entropy? I'll ask maybe Xavier. But before you answer it, I'll give you a hint. It's not SO3.
I would have to say maybe either. I'll go with KR.
KR, yes, that is correct. All right. So that means KR has the lowest, followed by Cl2, and then SO3.
Why is